Okay, so what you need to do is you need to search the internet for a Z-chart and know which chart you're using. So make sure you know which one you're using here. Okay, here's an application. I'm going to start you off with an application. A manufacturing process produces batteries with life expectancies that are normally distributed. So this is what you want to look for, normal distribution. And you're given that the mean is 500 hours with a standard deviation of 100 hours. And it says what percentage of batteries can be expected to last between the following intervals. Now, so the first one says between 500 and 670 hours. So what I want to do is find the corresponding area in the Z-table that goes along with 500 to 670 hours. So what I'm going to do is I'm going to go to a Z chart. I'm going to go to a Z chart. I know that 500 corresponds to Z equals 0. Well, that's just the mean. So that's the middle of the graph. So that would be, just this piece here. Okay? So that would be from there. Now, I want to find out to 670. Well, 670 corresponds to a Z-score of 1.7. Remember, you take 670 minus the mean divided by the standard deviation, and I get 1.7. So 670 would correspond to a Z-score over here at 1.7. So if I look up a table, and if I do the table that corresponds to this picture, and look up the Z-score, I actually, for 1.7, I'm going to get 0.45, roughly. It's actually, if you want to get more accurate, it's 0.4554. So that would mean that I would expect 45.54% of the batteries to last during that range. Now remember, if you use the other table, use a table that gives you a picture like this, it's giving you the area from the Z-score all the way over to the left. So you would have to take off 0.5 away from that to get the 0.45 or 4554. Now, the next one says between 350 and 650. Well, I need the Z-score for 350, which is negative 1.5, and then the Z-score for 650 is actually positive 1.5. So what I need to do is, since 650 is to the right of the mean, remember the mean is in the middle of the curve, and 350 would be to the left of the mean. Okay, so what I really want is I want the area from here over to here. But actually, if I just go to the curve and find the area between the mean and the Z-score of 1.5, now that'll give me this dark green area. Well, then I can just double it to get the entire area from negative 1.5 to positive 1.5. And that's due to symmetry, because this negative 1.5 has the same area between it and the mean as positive 1.5 has between it and the mean. So look up for positive 1.5, and I actually got 0.4332, but I want the area from negative 1.5 to positive 1.5, so double that area, and I get 0.8664 or 86.64%. Now the next one says greater than 670 hours. Now 670, we already know 670 is right here, and it corresponds to a Z-score of 1.7. I've got this wrong. So I've got the answer right. I've just got some copy paste that's gone haywire here. That should be 670 minus 500 over 100, which is 1.7. So we need the area to the right of 1.7 because we want the area greater than 670. So what we want is this little blue area. Is that right? Let's see. greater than 670. So we want this little bitty blue area here. Well, if I look up 1.7, that'll give me the area between the mean and 670. And we got this earlier to be 0.4554. Well, you see the green area under the curve? That's 0.4554. Now remember, we don't want the green, we want this little blue area under the curve. But remember, the area from the mean all the way over, that total area under the curve, is 0.5. So if I take 0.5 and subtract this green area off, it's got to leave me with the little bitty blue area here. So just take 0.5 and subtract the 0.4554, and it will give me the area to the right of 670, which is 0.0446. So it's 4.46%. And then the next one wants less than 750. So actually, if I want less than 750, I can plug in 750, which is 2.5. Okay, so less than 750, that would be this picture here. I want everything to the left of 750. Well, what I can do is just find this area here between the mean and 750, and then I can add the area to the left of it, which is 0.5, to that, and that'll give me the entire area. So I'm just going to look up this area over here between the mean and 750, which is, let's see, 750 corresponds to 2.5, and when I looked up 2.5 in the table, it told me that area was 0.4938, and then so the area between the mean and 750 is 0.4938, but I want everything to the left of 750, so I have to add in this 0.5 area to that, and when I add that together, I get 0.9938, or 99.38%. And then the last one there says between 650 and 750. So to find the area, here's 650 and here's 750. So what I can do is find the area between the mean and 750, and then subtract the area between the mean and 650, and what I will have left is the area between 650 and 750, which is that darker green area there. So I already know the area. The area for 750 is 2.5, so that's 0.4938. So the area from the mean out to 750 is 0.4938. So now the mean from the mean to 650 we know is 0.4332 from our earlier example. So if we take 0.4938 and subtract 0.4332, we'll get that the area in between 650 and 750 is actually the same area that's between z value of 1.5 and 2.5, which is about a little over 6%, 0.0606, which is 6.06%. Freeze the video and take a look at these practice problems, and then you can work these on your own. And once again, make sure you know which z table you're going to use to look up the z numbers. Sometimes a binomial distribution has numbers that really get too large to do. So what you can do sometimes is use a normal distribution in order to approximate a binomial distribution. Now there is some ambiguity in this, and you'll see it as we do this example. So look at example 1. Suppose we know a Major League Baseball player will bat 100 times, and we wanted to know the probability that he got less than 20 hits. Okay, let's assume his batting average is 0.3. That's 300 for you guys that aren't baseball experts. So the probability of success when he bats is 0.3, and the probability of failure when he bats is 0.7. Okay, so he's got 100 trials, so he's going to bat 100 times. If we use the typical calculations to find the probability that he gets less than 20 hits, we would have to find the probability that he got anywhere from 0 to 19 hits. And each of these calculations would require that formula for the binomial distribution that involves combinations and probabilities. So it would get kind of messy if we had to do each of these 20 calculations. So this is how we might use the normal distribution to actually calculate this. Okay, we know P, we know Q, and we know N. So if we know that, we can find the mean and standard deviation using formulas from the binomial distribution. Remember, the mean is NP, so we just do 100 times 0.3 and get 30. So the average, we would expect an average of 30 hits. And then if we use that formula for standard deviation, the square root of NPQ, we get 4.58. So it gets a little fishy here. Now I rounded to the nearest hundredth, but somebody else might round to 4.6, which will kind of change the answer a bit. And someone else might take it out to more decimals, which is 4.583. But anyway, I'm going to use 4.58. Now, what we want is we want the probability that x is less than 20. But if we use x equal 20, then that might include the 20. So we don't want to include the 20. So we're going to use a number close to 20 but less than 20. So I'm going to use 19.9. Now, somebody else might use 19.99 or 19.8, but I'm going to use 19.9. Okay, so I need the z value for 19.9. Well, we can use our z formula to get that. So, we use the z formula. We take 19.9 minus the mean, which is 30 from our calculation, divided by 4.8. So that gives me negative 2.21 for the z-score. Now, if I look up the area between the mean and 19.9, which is the area between the mean and 2.21 on the left side, I actually get 0.4864. I actually can look it up on the right side and get 0.4864, and then I can, I know by symmetry then the same value for 2.21 on both sides. That's the same area between the mean and 2.21 as it is between the mean and negative 2.21. Now, so I got 0.4864. Now, to get the area below 19.9, this is the area between 19.9 and the mean, but I want the area to the left of 19.9, so I can subtract 0.4864 from that, from 0.5, and that will give me the area to the left of 19.9. So the probability that he hits less than 20 hits is pretty slim. Now, I'll end this video by just letting you freeze it on a second example that I did, and then you can read it and work through it as a second example. Again, there's quite a bit of ambiguity on how far you round decimals and things of that nature when using a normal distribution to approximate a binomial distribution, but it shouldn't be off too much if you round to one place or two places. But that's just something you can depends on who your teacher is and how accurate they want the answer on how far you want to round things. So that's the end of the statistics videos, and the next chapter we'll do something new.